positions on the bases. I'm just going to show you one example. Before I do that, I just want to also mention that alkylation damage can also arise from endogenous sources as well as exogenous. And probably the biggest source of alkylation damage in a cell is the methyl donor, the metabolic methyl donor called S-adenosylmethionine, which you probably run across in biochem courses before. So cells have quite a high concentration of S-adenosylmethionine, and so occasionally that will result, because S-adenosylmethionine has a very reactive methyl group, it can result in base methylation. Okay, so the example I'm going to show you is here. This is O6-methylguanine, and here's the O6, and here it is methylated. And the theme is the same as what I've showed you before. On guanine, this is an H bond acceptor, and on the O6-methyl G, now this is nothing. It's neither an acceptor nor a donor. Here you have a donor, and on the O6-methyl G, now you have an acceptor. And so since you've changed the pattern of methyl donors and acceptors, you might expect that this would change the base pairing properties of O6-methyl G, and indeed it does, because what happens is that this change eliminates the specific bonding to cytosine. So normally you would have this pattern of methyl donors and acceptors resulting in 3 hydrogen bonds to cytosine, but this top acceptor here is absent in the O6-methyl G, right? So this specificity with cytosine is lost. It will still pair quite favorably with cytosine now through 2 hydrogen bonds rather than the typical 3, but it will also pair just as well with T, also through 2 hydrogen bonds. And so because now the O6-methyl G can pair either with C or T, when a polymerase sees that, it will insert, rather than 100% C, it'll insert 50% C, 50% T, because there's no hydrogen bonding discrimination now between the O6-methyl G and either of those bases. And then the pattern of damage and mutation is exactly the same as I showed you with the other examples. You have a damage event that alters the base pairing properties, and then when you take that through a round of replication, the O6-methyl G can base pair abnormally with T. If you take that through another round of replication, the polymerase that's copying the strand now has T, will obviously insert an A opposite it, and now you've got a mutation that has changed the GC base pair to an AT base pair. Okay, so let me just very quickly summarize, and then we can take a break. So I've showed you 2 classes of DNA damage that arise either from sources within a cell or external to a cell. I've showed you the loss of bases, changes of bases, and oxidative damage to bases can all occur spontaneously. CPDs and alkylation can be caused by environmental agencies, and the key sort of common theme is that these alterations to the bases change the base pairing properties, and this alteration of base pairing properties can then lead in a subsequent step that's dependent on DNA replication typically to mutation. I should also point out that these base alterations can also impede transcription and replication. So in the same way that DNA polymerase reads the DNA template, so does RNA polymerase. And so you might imagine if you have a big bulky lesion or a CPD standing in the way, transcription of that unit might not occur well either. And these also are impediments to normal DNA replication. Okay, so let's stop there and take